Hello everyone. Today it's the Tamhana show, but from a new perspective. Today you've got me, as you see here, in the other new office, and we are going to be talking about software coupling. And yes, I know object-oriented masturbation exists. This is not about it. This is about why software coupling is relevant for an electrical engineer, and also why making paradox decisions, such as running Windows on a Raspberry Pi, can make good sense. And to motivate, we have to accept that today's electrical engineering landscape is significantly more complex than it was, like, say, 10 years ago. You see, today, on the one hand, we have a rich presentation layer, a central server, usually gateways which are intelligent, and then finally we have the actual things which we control. And if things go badly, we've got 4 completely different operating systems and 4 completely different landscapes, which causes all kind of logical problem. And before we actually get into the video, I still wanted to give a hat tip to this guy. It's written by Ted Faison. You can sometimes buy the book used, and it's, even though it's a bit old and the Visual Basic examples, well, you don't want to touch that anymore really, it's still an excellent read and I can really recommend it. Well, sorry for the stupid perspective. Down there's a button. Like and subscribe. If you don't like and you don't subscribe, this channel can't grow and you miss out on all the scenes of me looking like a fucking ghost. So, you know what you have to do. Down there. So, now we are going to look at what coupling actually is. Coupling essentially is the relationship between any 2 elements. So in theory, if I touch my TV and I attach my hand to my TV, I'm coupled to the TV. And there are multiple in the IT space, different type of relationships. There is dynamic coupling, there is static coupling. And generally, the rule is this, that whenever we have a coupled system, changing one thing, like changing my position here, walking off the screen, would also affect the position of the TV. And as we know about the famous cube of ballistic gel, any kind of interrelation makes maintenance of the resulting system more difficult. And actually, research into coupling is not new. Here we have a definition which says the measure of the strength of association established by a connection from one module to another. And it's unbelievable, but this is from 1974, from a publication on mainframe software design, of all things. And when we at it already, there's also a second definition, and this is from Ted Faison, and it states that it is impossible to build a software system in which all components are completely decoupled from one another. So this means there is always some kind of coupling, just like there is always some kind of breathing in a YouTube video. But the job of the engineer is to mitigate the coupling risks so that we end up with the minimum amount of coupling in the system. So, and now, before we start our deep dive into the question what is coupling, I still want to introduce this symbol. It comes, as many other things in this presentation, from Ted Faison's book, and it says as much as the 2 objects are coupled together. And now, when it comes to our problems as electrical engineers, the amount of coupling problems which we can have is actually somewhat limited, because type coupling and signature coupling, which the compiler verifies, obviously doesn't affect us when we look at the structure which I showed before in the very first few slides. So this means that only logic coupling remains. And logic coupling means that the element A depends on element B doing something specific in order to successfully accomplish its work. And now, to round it off, we are going to take a very basic example. We are going to start off with a logger which sends data to the checker, and the checker then sends back a gaggle of optional settings. And in the first step, here we take a GigaDevice or STM32 controller. Well, with current availability, we're going to take GigaDevice. And over there, we have a classic stupid Windows app written in MFC. And we are using a completely custom protocol. So we run our measurement algorithm in C. We have STM32 or GigaDevice ints. We serialize them. We send the byte stream over, deserialize, use the other data format, and end up with a second copy of the algorithm, which is in MFC. And this situation is very bad, because if we look at this, if any one of these 8 elements fails, the situation is bad and basically the entire logging infrastructure goes up in fire. There is no verification possible by the compiler, so you better have 100% test coverage all the time, and trust me, normally it will also include manual tests. Okay, now I hear you people say, go, use JSON, Tam, use JSON, don't be stupid, use JSON. Well, if we use JSON, we don't need to worry about the integers anymore. But we still have to worry about the byte stream, the TCP stacks, and we also still have 2 copies of the algorithm. And this is not a good idea for multiple reasons, as I've said. First of all, the algorithm is very much still independent on both sides. And the problem is, testing an algorithm is not so simple, because when you are testing, normally you test the normal case. But the problem usually occurs in the edges, and these are notoriously difficult to test. And yes, of course, always the TCP IP stack, they just love to act up. Okay, now there is yet another approach. Some guy will say, oh, so use a framework. So now we are already limited in options, so we can't use our GigaDevice anymore, for example. We are going to assume we are going to use MicroAJ. Okay, MicroAJ is a very good example for a simple reason. The motto of MicroAJ is, we are Java for the microcontroller. The emphasis, however, is on the word for the microcontroller and not for the Java. So the thing is, some of it is similar, but some of it is also very different. And for now, we are going to assume that the TCP IP stack is shared. And so now we get this. We see the diagram already is very green, but we still have here 2 versions of the standard libraries. And the place where your algorithm interacts with the individual libraries is still yet another pain point. And this brings us to the final result. If we can run Windows on the target system, why don't we do it? We have completely the same code base everywhere. Windows here, and then everything is green, and basically this is all we need to worry about. So now it's time to wrap it up. First of all, if we code everything by hand, most things can go wrong. We get no compiler support, but of course we get the best performance. And equally important, if you're a consultant, you get the most revenue. If you write the entire system 2 times, you build a client 2 times, so you make the most amount of cash. But of course, you've got these problems. If we use a programming system, as said, we gain a lot, but we still don't gain everything. And the best solution would be to use the same operating system on all sides, maybe with a little real-time component, such as the one which was used in the Arduino Uno. And well, of course, the disadvantage is Windows, Linux, etc. are not very real-time capable. And if you only write the code base once, you can only build a client once. And this, of course, is a disadvantage if you want to sit in first class. And with that, I have to take the center stage again. I have to thank you all very much for being here and for listening for so long. This is the first fireside chat type thing which I'm doing in this facility, and I wanted to ask you, please, honest comments. Do you like this format? Do you find it interesting? Should we do it more often? And finally, are there any questions which are still unanswered about why I am so focused on Windows on Raspberry Pi, Java on microcontrollers, and these kind of topics? With that, once again, thank you very much for being a loyal watcher of this stream.